In our quest to understand the naive Bayes classification method, let's first understand what is Bayes' theorem. Now, Bayes' theorem is rooted in the concepts of conditional probability. So we need to understand Bayes' theorem in order to fully appreciate what the naive Bayes technique does. Okay, so let's understand Bayes' theorem. Okay, so again, back to our old uh, picture about people and people being buyers or non-buyers and people belonging to one of these three countries. So we already calculated some conditional probabilities. What is the probability that somebody is from Canada given that they're a buyer? We already know that there are this one, the moment we say given buyer, we are restricting our attention to this set of buyers. And out of that, what is the probability of them being Canadian? It's obviously this 3 divided by the overall number of buyers, which is 12. Okay, so we know this. So number of buyers and number of Canadian buyers. That's how you get this probability of Canada, given that somebody is a buyer. So that turns out to be 3 divided by 12, which is 3. That is the number of Canadian buyers divided by 12, total number of buyers. Okay, now we can also express this slightly differently, saying the same probability of Canada, given that somebody is a buyer, is this number of Canadian buyers by number of buyers. But just for argument's sake, let's divide both by 36. Okay, which is number of Canadian buyers by 36. What does that really mean? That is 3 divided by 36, right? Which is, what is this region? This region consists of people who are both Canadian and are buyers, right? So this is nothing but probability of Canada and buyer. Okay, I just said divided by 36 because we've got this region has 3 people, and to calculate the probability for this region we just divide by 36, right? That's because that's the total number, right? So effectively what we can do is just forget about the 36 and simply go by counts, and once you start dividing, things will come out to be the same, right? So the numerator represents, if you divide by 36, the probability that somebody is a Canadian and a buyer, and the denominator represents the probability that somebody is just a buyer, right? So probability of Canada given buyer is probability of Canada and buyer divided by probability of buyer. Okay, that is just saying the same thing, which is this divided by just the set of all buyers. This is an important step in understanding Bayes' theorem. So let's move forward. So let's consider this diagram once again. We already know that probability of Canada is 10 by 36 or 5 by 18. Okay, there are 10 points here, which is all of Canada, buyers and non-buyers together. There is a total of 36 points. So probability of Canada is 5 by 18, and probability of buyer is 12 by 36 or 1/3. Okay, and of course probability of somebody being a non-buyer is 2/3, because a person can be either a buyer or a non-buyer. Those two are mutually exclusive. Okay, so now let's consider this. Probability of Canada given buyer is 1/4, 3 divided by 12, we calculated that. And probability of Canada given a non-buyer is 7 by 24. There are 7 non-buyers in Canada, the 24 non-buyers overall. So that probability is 7 by 24. Okay, now just think about this. Probability of Canada given a buyer is 1/4. Probability of Canada given somebody is a non-buyer is 7 by 24. Okay, so of course we know that buyer and non-buyer are mutually exclusive. A person cannot be anything other than a buyer or a non-buyer in that dimension, in the status dimension. So therefore, it seems reasonable to think that these two, probability of Canada given buyer and probability of Canada given non-buyer, those are the only 2 ways in which somebody can be a Canadian in this example, right? Shouldn't those 2 add up to the probability of Canada, right? Because you can either be a buyer or a non-buyer. You've got these 2 probabilities. If you add them up, you should get probability of Canada. It looks like it, but you don't, right? Because if you add up 1/4 and 7 by 24, you don't get 5 by 18. Okay, the reason you don't get it is that this probability is based on, given a buyer, is based on 3 cases. Okay, and this probability is based on 24 cases. Okay, so therefore, if you weight them suitably, it'll work. right? So this has to be weighted by the probability of buyer, and this has to be weighted by the probability of non-buyer. And then if you add them up, you will indeed get the probability of Canada, right? So therefore, in general, you can say this. You can say probability of Canada is probability of Canada given buyer times the probability of buyer. So we are weighting this by the probability of buyer, okay? And this we are saying probability of Canada given something other than buyer. I could have said non-buyer, but what if there were several classes, buyer, non-buyer, undecided, etc. So in general, I'm saying probability of not being a buyer times probability of not being a buyer. That is probability of Canada given the person is not a buyer, meaning anything else, times the probability of that anything else. In this example, it's only non-buyer, right? So effectively, that will add up to probability of Canada. So effectively, what we have said is probability of Canada given buyer is probability of Canada and buyer divided by probability of buyer. Okay. Now, of course, when you put things in mathematical terms like this, suddenly it starts losing meaning. Okay. So let's go back to the reality. So probability of Canada given buyer is this probability of Canada and buyer divided by probability of buyer, right? So effectively what you're saying is the moment you're given buyer, then our attention is restricted to this area alone, which is buyers alone. So that becomes the denominator, which is probability of buyer. And the numerator becomes within that set, what is the problem? Who are the people from Canada? Nothing but probability of Canada and buyer. Okay, so that's all you're saying here. Probability of Canada given buyer is probability of Canada and buyer divided by probability of buyer. Okay, in general, probability of A given B is probability of A and B divided by probability of B. Okay, likewise, you can also say the same thing the other way. Probability of B given A is probability of A and B once again divided by probability of A, right? That is because probability of A and B is the same as probability of B and A. Okay, it doesn't matter in what order you state it because you're saying both those things are happening. Okay, so probability of A given B is this, probability of B given A is that. Okay, and therefore you can say probability of A and B is probability of B given A multiplied by probability of A. Just rearranging this, right? If you take this over to that side, you multiply this and you get this. Probability of A and B is probability of B given A times probability of A. Okay, and of course this says this because probability of A and B is nothing but probability of B given A times probability of A. So probability of A given B is probability of B given A times probability of A divided by probability of B, right? That is because all we did was we replaced A and B by this because this is A and B. Okay, and this is one way of saying it, and effectively this is Bayes' theorem. Okay, and we'll see why this is so important for the naive Bayes method. Okay, and of course you can say it like this because probability of B is nothing but probability of B given A times probability of A plus probability of B given not A times probability of not A, which is just what we found on the previous page. But for now, let's just focus on this. This is not that important for us for now. Okay, so what this does is it allows us to express probability of A given B in terms of probability of B given A. Okay, so automatic question is, so what, right? So what if you can express it like this? This is the crux of Bayes' theorem, of naive Bayes method. Okay, and we'll see this shortly, why this is important, right? So effectively, from all of this discussion, what you really need to take away is that the Bayes' theorem allows us to express probability of A given B in terms of the reverse conditional probability, that is probability of B given A. Okay, why is that important? We'll see shortly. Okay, so if there's only one thing you take away from Bayes' theorem for our purposes, let it be this, that it allows us to express one conditional probability in terms of the reverse conditional probability.